Everyone, I am Sneha and this is day 30 of 30 days of building with Solidity. 30 long days. You made it. 30 full days of diving deep into Solidity, one contract at a time, one concept at a time, from your first event to your first token sale. You have been showing up, building, learning, and now you are ready to create the thing that powers everything from DeFi whales to yield farming degens, which is a decentralized exchange, your own MiniDex. But before we go any further, let's first take a moment to appreciate it. Like, seriously, look back at day one. You started with basic storage, structs, functions. You learned about global variables, control flow, modifiers, inheritance, interfaces, and whatnot. You got hands-on with NFTs, DAOs, AMMs, stablecoins, oracles, randomness, upgradable contracts, and more. And you didn't just read about them. You built them. This wasn't a read and forget kind of series. This was write, debug, understand, break, fix, deploy, all of it. That's real Solidity muscle that you've grown, and we have grown with you. And now on day 30, it's time for your Capstone project, a mini decentralized exchange. So if this video supposedly goes viral, okay, or any one of you who have not seen me in any other videos and this is where you land for the first time, we did a campaign, 30 days of Solidity, where we took all of these people who were with us in the community, from storage variables to data types to functions, all of it, to building like 9 real world applications. So that's the entire series. You can either go to our day one video, that is where we talk about the entire campaign in detail. That is where we pour our hearts out and tell you what vision we have for the entire campaign without even knowing if we were capable to actually complete it. But here we are. And in case you're really lazy to go through the entire playlist and find day one, you can head over to web3compass.xyz, check out a lot of things, but here 30 days of building with Solidity, and that is day 30. I mean, look at it, from fundamentals to intermediate to advanced to actually building real world applications. Oh my God, pat on the back. All of you deserve a vacation, a mini vacation, just a day to be proud of yourself that, yeah, you did it. And I know so many of you in the community who have been doing it for the past 30 days. Super proud. Consistency is one thing that everybody struggles with, and you have done it. So yeah, glad. Okay, so now let's talk about the mini DEX that we're going to build. So we're going to build a simple exchange for trading tokens. You will learn how to create digital marketplace using token swaps and liquidity pools. It's like a mini version of a stock exchange, demonstrating how to create a decentralized exchanges. Now, this is not a copy paste. This is not a copy paste Uniswap clone. We're talking a very clean, simple, stripped down from scratch implementation of a DEX. Just enough to understand how swapping liquidity and liquidity pool tokens really work. This isn't front-end stuff. I suck at front-end. This is the on-chain backend of a DEX. Please feel free to add front-end and make it a full-fledged project. We are going to talk about the smart contract logic, the vault, the pool, the price curve, and all of it. And to make it all click, we are splitting this final challenge into two contracts. One is a MiniDex pair.sol, which is the pool contract. That is where the action happens. It takes in two tokens, token A, token B. It allows users to add liquidity, and in return, they get LP tokens. Again, I think we've done this in the lending pool. It allows users to remove liquidity and get back their proportional share. It enables swaps between token A and token B using the classic constant product formula X into Y equals to K. It keeps tracks of internal servers, LP balances, and fees. This is the core logic that runs every token pair, whether it's ETH DAI, USDC, WBTC, or any other combo that you're talking about. We go deep into how this works, how fees are calculated, how reserve updates keep the pool balanced, and all of it. And the second part of the contract is MiniDexFactory.sol, which is the pool creator. Once we understand how a single pair contract works, we'll take it to a next level. Instead of manually deploying new contracts or new pair contracts, for every token combination, we will build a factory that can create new MiniDex pair contracts dynamically, keeps track of all existing pairs, ensures no duplicate pools. Let us explore how protocols like Uniswap can scale to thousands of pairs. And by the end of this lesson, you will have a working mini version of a DEX, the ability to deploy any pair that you want, a full understanding of how swaps, reserves, LP tokens, and AMMs work under the hood. And more importantly, you will realize that these seemingly complex protocols are just smart contract patterns composed from tools you already know. So one last time. No. Not exactly the last, but yeah, for this campaign last, let's write a contract, let's learn something real, and let's end this journey with the same energy that we started on with builder mode on. Let's dive into MiniDexPair.sol. We'll head over to Remix. Oops, I've not closed my previous files. Okay. Yeah, some things never change. So I'll create a file which says MiniDex pair.sol. Okay, that's one thing. Now, before we get into the how, let's understand why, what. Okay, so the MiniDex pair contract is the engine that powers every token swap on our MiniDex. It's the vault, it's the liquidity pool, the LP token calculator. It's responsible for holding two tokens, letting people swap between them, and managing the internal reserves that keep the entire or the whole system fair and fluid. You can think of this as your personal token exchange booth. Put in token A, get out token B, priced automatically based on supply, demand, and some simple but powerful math. And we'll break down every function in detail like we've been doing. Let me just copy this, save it here. Okay, great. So we have to actually import two things. Again, IRC20.sol and then reentrancy guard. Again, as of now, you know what both of these mean. Okay, and for everyone who has done the lending pool, yeah, I mean, this should explain everything what we're going to talk about, at least the first pair contract that we're talking about, because we're going to write the same functions: square root, minimum, update reserves, add liquidity, remove liquidity, swap tokens, get amount out, etc., get reserves, get LP balance, blah blah blah. And then we will move to the next part. Okay, so the first part, which is these imports, again, IRC20.sol brings in the interface for the ERC20 standard. In plain terms, it tells a contract how to talk to any ERC token, even though we didn't write the token's code ourselves. With this interface, we can call transfer from, transfer balance of any compliant ERC20 token, use those tokens in our liquidity pool, stay fully token agnostic, DAI, USDC, W, ETH, whatever. It all just works. Without this import, Solidity wouldn't know how to talk to all the token contracts you pass in. Okay. Reentrancy guard, again, it's for security. It helps us protect against a class of smart contract attacks called reentrancy attacks, where someone tries to call back into the contract before the function call is done. Again, so reentrancy, go watch our Fortnox video. We talk about it in detail. For the first part, which is the MiniDex pair here, again, liquidity pool, lending pool, and how things are working, go watch the lending pool video. You will get to know it. But yeah, anyway, we're going to talk about all of it here, so no worries. Now we'll just declare the contract and we say, hey, contract MiniDex pair is the reentrancy guard, and then we'll just get started building. Okay, so I say contract MiniDex pair is reentrancy. Great. Reentrancy. Okay, fine. So we're talking about state variables here, which is like the pool's memory. So we will say address, public, immutable, token A. Great. The same thing. I don't think there's a need to explain this contract again, but yeah, like it's a part of the DEX solution. That is why we are talking about it. Then we say uint 256 public reserve A. Okay, great. The same for reserve B, and then there will be a total supply. Okay, so let's make this reserve B, and let's make this a total supply. Great. Now I don't need to explain you what address, public, token A, immutable is doing. Each MiniDex pair contract will only ever deal with exactly two tokens, DAI, ETH, USDC, ETH, or whatsoever. They're marked public, so anyone can read them, and immutable because once it's set through the constructor, they can never be changed. Again, reserve A, reserve B keeps track of how much of each token is currently in the pool. Whenever someone's add liquidity, does a swap, or removes liquidity, we update these reserves to reflect the new balances. And they're not, these are not just actual token balances in the contract. We keep them stored separately for two reasons. Again, the read efficiency would be better. It's faster and cheaper to reference variables and to keep calling balance off. And price accuracy also, because we are working on a constant product formula, x into y equals to k, so it stays balanced. Okay, now total, actually this one has to be a total LP supply, because we're talking about liquidity pool tokens only here. Token A, token B would be deployed separately. So again, total amount of LP tokens ever minted, kind of like the total shares of the company. So when someone adds liquidity, we mint LP tokens for them, not actually RC20 tokens in this case, but just tracked internally. Okay, now there would be a mapping, which it's like how we keep track of how much liquidity each user owns in this pool. So we say address, mapping. Okay, address, and then we say uint 256, and then we're saying public LP balances. So this is going to talk about how much balance LP, like liquidity pool balance, does each person or user holds. Okay, so these are more around the variables. Now obviously there would be certain events that will be emitted, so we say event liquidity added. Okay, we're saying address indexed, who is the provider of the liquidity. Great. Then we say uint 256 amount A. Okay, uint 256 amount of B, right? And uint 256, how much LP is minted. Okay, great. Now, if liquidity is added, it will also be a scenario where liquidity is removed. Okay, so let's talk about who is the provider again, how much amount A, how much amount B, and uint LP instead of minted, we're saying burnt. Great, fine. Now we're saying event swapped. Okay, because we're swapping tokens as well. So we're saying address indexed user. Okay, we're saying address of input token, then address of, no, we can say uint 256, like we'll keep the input part together, input amount, then we say address output token, and then we say uint 256 output amount. Great, fine. So again, on-chain logs don't really affect the contract logic, and yeah, I mean, lets us know everything very, very transparently. And all of these are like self-understandable. Liquidity added, removed, who did it, who removed, how much of each token did they withdraw, how many LP tokens were minted or burned, and whatsoever. Now it's time we write the constructor. Okay, let's do it. So we're saying constructor, and then we're saying address of token A. Yep. Token A, because this will be the contract address of our token A that we have created, and then there would be a token B. Fine. And then what we're saying is we'll put conditions. Last time we did not, that the token A address should not be equals to token B. Okay. Again, that becomes identical address, right? So we say identical address. Great. And then the other thing to check is the address 0. Now, you could have done a custom error, but yeah, it's not happening again and again that we're checking this, so doesn't matter. Not equals to address 0. And we're saying token B not equals to address 0, otherwise it becomes a 0 address, right? Great, conditions checked. Now in token A, we will write token A, great. Token B, we give the value of token B. Great. So this function is only going to run like only once. We pass in the 2 token addresses. This pool should support any tokens, and we're checking if they are not identical token addresses, and then they're not 0 addresses. Okay, and now finally we assign the input values to the contract's immutable state variables that we had declared, and because they're immutable, they can only be set once. So this ensures each contract instance is permanently tied to just 2 tokens. Nobody can mess with the token addresses after the deployment functions. Now, what happens is, even for lending pool, now I've lost all my 30 days of Solidity files, so I don't have it here. But lending pool talked about 2 functions, one minimum, one square. Okay. So I'll tell you why. Okay. Actually, I won't. You should just go watch that video. That why are we talking about, these helper functions? Why do we need it here? So we're saying return A less than B, and we're using a ternary operator, and we're saying, okay, great. That is one thing. Again, other is function square root. And we're saying uint y. Again, this is Babylonian method. You should know it. For everyone who has watched that video, should know it. Returns uint z. Okay. Now, for everyone who has watched this video, I am sure that you might be able to recall why the square root thing came into the picture, and how we said that if you're the first person to add liquidity in order to maintain balances, you would give if you've deployed, like if you have a reserve of 100 tokens of A and 100 tokens of B, the liquidity pool token provided would be a square root of 100 like tokens A and tokens B, right? That is what we do. And yeah, also to maintain a constant for both, like x into y equals to k, and maintain the pricing, we'll choose to mint the LP tokens based on which token is with a minimum amount, and that is why we use the minimum function. Yeah, there, said it. I was not supposed to say it. Y by 2 plus 1. Again, I am not explaining this. Go to that video. Skip to the section where I talk about it, blabber out loud, and that is how you're going to understand. I've already showed you which video I'm talking about. So y by x plus x and the whole thing divided by 2. Okay, great. So this was a while condition, and then we are saying else if y is not equals to 0, we're saying set equals to 1. Great. Yeah, fine. Yeah. So again, it's not like a square root calculator. We use this function when the very first liquidity provider entered the pool, no tokens in the reserves yet. We can use proportional LP calculation. That's where it happens. Minimum one, very straightforward. To keep the pool ratio intact, we only consider the smaller effective contribution. Great. Now we will write another function called update reserves. Okay. So we're saying function. Now this is going to be a private function. Update reserves, and we're saying private. This function is simple, but it plays a very key role in maintaining the integrity of the pool. What it does is, I'll show you what it does. It's like an internal tracking variables by actually reading how many tokens are sitting in the contract. So we're saying IRC20 token A dot balance off and address this. The same thing would go for reserve B is equals to, come on, why is it not suggesting? The same thing, but this will be token B dot balance off, address this. Okay, so these are like true balances of each token which is held by the contract at any moment. We store these values in reserve A, reserve B state variable, so we don't have to keep calling the balance of function over and over again. And cost more gas. Again, it's marked private because this function isn't meant to be called directly by users or external contracts. It's an internal helper used by functions like maybe add liquidity, remove liquidity, swap. Because anytime tokens move in or out of the contract, we call update reserves to sync up the numbers. This keeps the internal state accurate and ensures that all our math and calculation that we're doing behind is, especially in the case of swap calculation, is based on the latest actual balances. Okay. Now we are going to write function add liquidity. Okay. So we are saying uint 256. Amount A, uint 256, amount B, and this becomes external, also non-reentrant. Okay, now what happens? What happens is you have to check, okay, that amount A is greater than 0, and then amount B is greater than 0. Otherwise, we're going to say it's an invalid amount. No need of explanations here. Then we will take, we will take this IRC20 token A dot transfer from, again, In order to understand from where this transfer form is coming and what it means and all of that, go to our ERC20 contract. That is where we talk about this entire thing in detail. Similar for B as well. This will be B transfer from message.sender, address this amount B. Great. Okay. Now what we will do is we will take LP to mint. Okay, so we have to calculate how much liquidity pool tokens need to be minted and how are we going to calculate. So this is where it comes into the play that if the total LP supply is 0, that means you're the first person adding it to the liquidity pool. So LP to mint will be, oh God, no. Okay, LP to mint is not going to be minimum. It is going to be the square root of amount A and amount B. That's it. Okay, for the first one, that's what it is going to be. And that is why we calculated expected 1. Oh, not comma. Yep, great. Okay, so now that is why we wrote the square root function. Now if you come to else, okay, we say LP to mint is equals to minimum, and this is where the minimum comes into play. So we say amount of A into total LP supply. Oops. There will be a parenthesis here. Great. Yeah. By reserve of A, because we're calculating the minimum here. Okay. And then we will take a similar thing for reserve of B. Again, this is what helps maintain the constant value here. Okay. Fine. Now what you do is you just have to check condition that LP to mint has to be greater than 0 or 0 LP to be minted. Fine. Now what you will do once you've done everything, you take the LP balances for this message.sender plus equals to LP to mint, and then you say total LP supply plus equals to LP to mint. Okay. And then you call the update reserves function. Again, this was private. And then you say emit a liquidity adder. Who's the provider? Message.sender. Amount A, amount B. And this is LP to mint. Voila. Very simple. Again, same as what we did for the lending pool. Okay. So just quick. You check the conditions for both amounts to be greater than 0. You pull in the token with IRC20 line. So this pulls both tokens from the user's wallet into the pool. Disclaimer, the user while deploying the ERC20, like after deploying, must have called approve beforehand for both of these token transfers to happen, and that will be called for this particular contract address. Now this is where the next step where all the math kicks in. We have to figure out LP to mint. So we will check if there's the total LP supply is 0, go for the square root logic. If there's a subsequent deposit, we use the minimum logic to ensure that the liquidity is added in the correct ratio and LP tokens are minted proportionally. Okay. Final check, state update again. Require LP to mint greater than 0, then put it in the message.sender, like mapping LP to mint, and then increase the overall LP supply. Great. Then update reserves again. This syncs the pool's internal state with the actual token balances, making sure all the future math is based upon the current balance and up-to-date values, and then you emit the event. Great. Okay. Now, I know this was fast, but come on, we expect you to understand all of this and not even having the need for us to write this because we did an entire lending pool thingy. Okay. Function remove liquidity. Okay. So we're saying uint 256 256 LP amount. Great. External non-reentrant. Okay, great. Okay. Now what happens? You check if the LP amount is greater than 0 and the LP amount is less than equals to the LP balances for the message.sender, because or not this message.sender, message.sender. Okay. Otherwise, we're saying invalid amount. Cool. Yeah. Okay. Once you have done that, you say UNT 256 amount A. Okay, is LP amount into a reserve of A divided by total LP supply. Great. So that's UNT 256 amount A. And the same goes for B. We just say it's reserve of B and total LP supply. Great. Now, because we are removing the liquidity, right, we will take LP balances for the message dot sender and then we minus equals to LP amount. Wow, smart. And then we also reduce it from the total LP supplied. Exactly what we did here. Now we will transfer it back to the wallet of the user. That is why we are not using transfer from, but instead transfer and then message.sender, not to this contract. So message.sender amount A, message.sender amount B. Voila, done. Again, update reserves. Okay, update reserves. And then what? Emit liquidity remove from who? Message dot sender. And then it's amount A, amount B, and then LP instead of burned, we're saying LP amount. Yep, that quickly. We did it that quickly. Same. Check the condition if the user is actually trying to remove a positive amount. They're not trying to remove more than they own. Implement the proportional share formula. If you own 10% of the LP supply, you should get 10% of both the tokens reserves back, right? That is what we're doing here. What is the amount of A? LP amount into reserve A by total LP supply. Same goes for B. And then you burn the LP token. So you subtract it from message.sender, you subtract it from total LP supply. So the user's LP balance goes down. The total supply of LP tokens goes down as well. And then this like simulates burning the LP tokens, and then you do the token transfer back to the user. Again, using the transfer function, message.sender amount, sync the internal reserves, and emit a log for transparency. How smart. Okay. Now, if we, next we're going to write a function called get amount out, okay, which is calculating swap out. Before we actually perform a swap, we need to know that if I give the pool X amount of token A, how much token B will I get back? That's exactly what this function is going to do. It uses the constant product formula to calculate a fair output amount based on current reserves. Okay, let's get going. Function get amount. I don't think we wrote this one. I think we did. Okay, so we're saying input amount, and then we're saying address of the input token. Okay, and we're saying public view returns what? UNT 256 output amount. Fine, very simple. Take the address and input amount and then give back the output amount. Okay, require that the input token is equals to token A or input token is token B. Otherwise, invalid input token. Very smart. Bool is token A is equals to input token equals to token A. Fine. We're saying UN 256, okay? Input reserve, okay, comma, UN 256, output reserve. Now, this is something new that we are doing here, okay? Like we're using a ternary operator, okay? See what we say is token A, question mark, reserve A, comma, reserve B, okay, colon, or the other way around. Reserve B, comma, reserve A. Wow, what did we just do? Huh? So we checked the token validation should be there. The user must be swapping either token A, token B. We identify the input and output sides of trade. Okay, so we determine which direction the trade is going. We declare a variable is token A. Okay, so when we're doing input token equals to token A, we're swapping A to B. Otherwise, we're swapping B to A. Then we extract the correct reserves accordingly. Okay, that is what is happening. True? Yeah, this. False? This. Great. That is how we get the reserve. Now, we apply the swap fee. So we say UN256 input with fee is equals to input amount into 997. Again, we're keeping a 0.3% cut, just like Uniswap V2 does. The full input amount would be input amount into 1000, but we only use 997, keeping 0.3 inside the pool as protocol fee. Again, this small fee makes DEX liquidity sustainable, rewarding LP with swap fees. Now we're going to calculate the output using the AMM formula. Again, core formula, x into y equals to k. So we say, yeah, UN256 numerator is input with fee actually. Input with fee into output reserve, oh my god. Okay, and then we have a denominator. So we say denominator. Yeah. We say input reserve into 1000 plus input with fee. Okay, and then we say output amount is gonna be numerator. Wow, how cool. Denominator. Yeah. So we're saying again, core formula, input, output, reserve into 997, input, reserve, blah, blah, blah. So this ensures that the more you try to swap at once, the worse your price becomes because of slippage. The pool never gets drained completely. Swap always leave the product X into Y roughly the same. Okay. This function is again read-only. It doesn't move any tokens. It is meant to simulate what a swap would yield before you actually, do it. So then we say, let's do the function swap. Okay. This one we've written again. Earlier we did function swap A to B, B to A, two different functions, but here we are writing one. So we're saying uint 256 input amount, again, address, input, token, external, non-read, and okay, a lot of things here is gonna be the same. Okay, so we're saying fine. No, this. Swapping token A, token B, fine. We're saying, okay, require first, the input amount has to be greater than 0, otherwise it says 0 input, fine, and then require, okay, this is it, okay. We say, fine, input token is equals to token A or token B, otherwise it's invalid input token. And then we say address output token is equals to, again, ternary operators here. So we're saying input token, we have to check if it's equal to token A. If yes, great, then the output would be token B. Otherwise, it's token A. Fine. You should know how ternary operators work. This is supposed to be the result. This is the condition that's matching. So if this becomes true, this is the answer. If this becomes false, then this is the output. So then output token would be token A because our input token is not token A and vice versa. Okay. And then you say uint 256 output amount is get amount out, input amount, and then input token. Okay. And we say require, again, before IRC20, I say require output amount is greater than 0, and then otherwise it says insufficient amount. Output. I'll be confused. Okay. Now that this has happened, we're swapping, right? So, okay, one would use a transfer from and the other would use transfer. Okay. So let's see. We are saying we need the input token, actually just input token, and then we want that to transfer from message.sender address this, okay, comma, there should be an input amount. Fine, great. And the output token should transfer from message.sender and output amount. And then we say update reserves. Great. So the internal sync is also happening. And then we say emit swapped. Again, who's the user? Message.sender input token, input amount, output token, output amount. Great. Now, what just happened? Two condition checks. Make sure that the user is sending a non-zero amount, one of the two valid pool tokens. Determine the output token. I've talked about it. If input is token A, the output is token B and vice versa. Calculate how much to send back. Now, its output token is get amount out. We're using that function here, doing all the calculation, and then we check if the output amount has to be greater than 0, otherwise it's an insufficient amount because the AMM formula has to be maintained, okay, and the current reserves to calculate a fair price including the 0.3 fee. If the result is 0, maybe because the input was too small, so we just revert. And then we transfer tokens. We actually move tokens, so we pull the input token from the user into the pool, send the calculated output token back to the user. This is the real swap in action. Sync the reserve, emit a swap event. Yeah, so you've completed the entire logic for working liquidity pool, add liquidity, remove liquidity, calculate fair prices, execute token swaps. Now we're going to quickly write a lot of view functions. Okay, so we will say, again, favorite function, get resolves. Oops. Yeah. External view returns uint 256, uint 256, and we say return reserve of A, comma, reserve of B. Correct. That's one. Function get LP. Oops. Get LP balance, again, address of the user, external view returns uint 56. Great. Return LP balances, and then we're saying user. Great, another one. Fine, and this is the last one. Function, get total LP supply. Okay, external view returns. Uint to 56, and we say return total LP. Okay, so you know what all of these are doing. First one is giving us results. Second one is giving how many LP tokens a given address holds, essentially their ownership stake in the pool. And then the other one is total LP supply. So check how much of the pool any single LP owns via user LP. By total LP, visualize how the pool is growing over time. And with that, the MiniDex pair contract is complete. Now, you now have a full working DEX pair, supports ERC20, lets user swap, add, remove liquidity, calculates prices, says using a constant AMM model, emits very clean events, and exposes helpful view functions. Okay, now you can do a deployment around here, MiniDex pair in Remix step by step. Okay, but we have to install or import two ERC20 mock tokens here. Let's call them like token A, token B. So we'll just quickly deploy it. Okay, and now once we like deploying it, right, like we've said, okay, there will be a new MiniDex pair contract, compile it, deploy, pasting the two token addresses that you're going to get. Okay, so this is token A. Let me also just copy this and create another file. Token B.sol. Okay, close. And then here we say B and TK. Okay, great. So we compile this. Let's keep it here. We change it to mainnet fork for the last one. Oops. Oh, sorry. Compile it. Okay, deploy. That's one. Let's go. Compile. Deploy. Let's go. This is the MiniDex pair. Compile. Okay. Address of token A and address of token B. So this was token B. That is what we copied first. Great. Address of token A. Great. Transact. Fine. We have our MiniDex pair also deployed. Okay. Now what we're doing is we have to approve function on both token contracts, token A as well as token B, to send it to the contract, right? So we will go to token B and we will say, hey, we can just approve value for 1000 tokens again with 18 zeros, and we will paste it here also. And the address is going to be this address, right? You see how smart I am? Copying one, pasting twice. Yay, let's go. So I transact this. So we've approved it, right? And then we come here and we say add liquidity. Okay. Add liquidity. So we're saying maybe 100 tokens if we have approved like 1000 or whatsoever. So I will just copy this and I will say, can I paste it here, but remove 10, and the same for this, but I will remove, oh, where did I copy it from? Yeah. And I'll make this 200. Can I do this? Okay. Reserve A, reserve B, token A, token B, total LP supply. Great. Get reserves. Great. Okay. So we have deployed two token addresses, token A, token B. We've gone to that one to approve the DEX contract to like transfer tokens, and we've approved or added liquidity of 100 token A and 200 token B. And yeah, we've added that liquidity. You can check get reserves, and you can also get LP balance. Just copy this account address from here. Where am I? Where am I? And yeah, because that's a total LP supply. Yeah, you're getting it as a square root. So yeah, square root of 2 is 1.414, and you see we've taken like 100 tokens here, 200, a square root of that with 18 zeros, 1414. Yeah, that's how you see it. Okay, now you can also swap. So what I will do is I would say input amount, input token. So because we've added what? Amount of B. Okay. So we want A more. So I would say, okay, yeah, swap input token here. And I will say let's swap maybe 50 tokens instead of 100, right? So I remove one more, and yeah, that becomes 50 tokens. We have 3, 3, 6, okay, 3, 3, 6, 3, 9, 12, 15, 18, yeah, 50 tokens. We transact. So now reserve of A reduces, reserve of B increases. We have learned about this in the automated market maker thingy as well. Oh, you should watch the AMM video as well. Yep. Yeah. So we have learned this, that is how AMM works. Whatever reserves or whatever you're swapping, that's value will increase in the contract, and the value for other one would decrease. Okay, whatever input, like amount input token, and then you can just go remove liquidity, play around. Okay, now the agenda is to make this a dynamic. Okay, so that is where we enter the MiniDex factory. MiniDex factory dot so correct. Okay, so up until now our MiniDex pair contract has been solid. It works beautifully as a standalone tool, but here's the catch. Every time we want to create a new token pair, say Difrax, Pepe Sol, ETH USDC, we have to manually deploy a fresh copy of the MiniDex pair contract. And that's fine if you're building one off prototype, but in the real world of DeFi, DEXs doesn't just support one trading pair. They support hundreds, sometimes thousands, and all of them need to be deployable on the fly, discoverable and indexable and reusable by other contracts and front ends, right? So what do? We introduce a factory, a smart contract that can deploy new pools, track them, make the whole DEX system dynamic. That's exactly what MiniDex Factory is supposed to do. This contract becomes the central registry for all the pairs in our DEX. With it, we can create new token pairs on demand, prevent duplicates, retrieve the address of a pair using just the token address, loop through all the pairs if needed for analytics, UIs, etc. In short, this is how we scale from one pool prototype to a fully functioning decentralized exchange. Okay. Now, that we've built like the MiniDex pair, it's time to scale, obviously. So let's get started with writing the MiniDex factory, right? Okay, so what we will do, okay, we will copy it from here first, paste it here. Okay, there are two imports that we're gonna make. Again, I'm not sure if we, yep. Okay, so there's one import that's going to be an Open Zeppelin, and the another is going to be importing the MiniDex pair contract. Now you have to make sure that MiniDex pair.sol is in the same directory. Okay, and we're saying contract MiniDex factory is ownable. Again, we've talked about what ownable is here with Open Zeppelin and what this means, when you're inheriting it, right? So it sets up everything the MiniDex factory needs to function safely and efficiently. So ownable again comes from Open Zeppelin. It gives our contract access control. By inheriting from ownable, we can automatically track the contract's owner, restrict sensitive functions like create pair to be only called by the owner or the admin, and use the only owner modifier for security. And again, MiniDex pair.sol is a local import. It brings in the pair contract that we've written earlier, and the factory's whole job is to deploy new instances of this contract for different token combinations, right? So anytime we're gonna call the create pair function, which we're gonna write, we'll be spinning up a fresh MiniDex pair, passing in just 2 token addresses we want the pool to support. The key point here is the factory knows about the pair contract and uses it as a template, kind of like minting a new pool every time someone needs a new trading pair, right? So, yep. Let's think, right? Let's think of the state variables, the events, what happens. Okay. So I cannot think of any variables, but what I can think of is a mapping and an event. Okay. So maybe let me write the event. That is what I can think of first, right? So we say pair created. That's the whole base of it, right? Central hub for pool creation. It needs a reliable way to track, store, expose the data behind every MiniDex pair, right? So we're saying address, indexed, token A. Again, address, indexed, token B, address, pair, address, and then a event, okay? Yeah, that's all. That's all I can think of. And then there's a mapping. But what is it that is happening here? Token A, token B, the 2 tokens in pair indexed again, so you can filter them. Pair address is the actual deployed address of the new MiniDex pair contract, a event that acts as the pair's index in the all pairs array that we're gonna do, right? Now, incredibly useful for front-end apps trying to display all available pairs, indexes, tracking pair creation on chain, developers debugging deployments, whatsoever, right? Now we will have to create a double mapping for get pair, okay? So the double mapping is going to be able to store the deployed address of every pair that gets created, right? Like get pair, die, weth, 0x, blah, 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 pair address. Get pair, weth, die, 0x, blah, blah, blah. Get pair, USDC, ETH, yeah, that's the address. So both directions are stored so users can query their pair regardless of token order. More on that in create function that we'll write. But it has to be supposed to be marked public. So we're saying address, and then there's mapping, and then address to address. Wow, too many addresses. And then we say public get pair, right? Fine. Okay, so now you can call get pair token A, token B at any time to check whether that pair exists and retrieve the deployed pool address. Okay. Now there's also gonna be an address array for public all pairs, which will keep all of the pairs that has been deployed, all the pair contracts ever created by this factory. Each time a new pool is created, it gets pushed into this array. It allows looping through all created field pools, returning pool address by index, building, UIs and all of that. So with just 3 lines, we're just gonna write a way to log every new pair, a way to store and look up each one efficiently, and a way to list and count every pool in the system. Okay, let's try that. We'll have a list of addresses, public, all, pairs. Yep. Okay, now that we've thought of it, it's time we do the constructor, right? So we say constructor address owner, and then we say ownable, and we have to provide the argument here. Like again, we have to pass the address directly, because that is how the Open Zeppelin format works like. Okay, so we accept an owner address as input during deployment, and we pass that address directly to the ownable constructor from Open Zeppelin. So what is the result? Whoever deploys the contract, they can assign ownership to someone else immediately. Okay, so that's all with the constructor here. Now we should just get writing like create pair, right? That is one function that we all have been really looking forward to, because that's the main thing that we want to do here. So, oh, did I just give this? Yeah. Okay. What happened? Constructor address. Yeah. Oh, not this. Actually, this will just be like this. Yep. Yeah. Okay. So then we say, okay, let's write create pair. What's gonna happen? Okay. AI is suggesting something. Function create pair address token A, address token B, external, only owner, great, returns address pair. I don't want the entire thing. Okay, great. Now what? It's not checking anything here. Let's just remove it. When will AI be able to help us? Come on, come on. Yep. Okay. So we're saying require token A. Actually, yeah. Smart. Yep. Sorry guys. AI. Yeah. So we're checking token A not equals to address 0. Token B is also not address 0. Token A and token B are not identical tokens. And another required condition which is new is that we say get pair, and then we say token A, and the other part is token B. Okay, this is equals to address 0. Right. And then we say, hey, pair already exists. Okay, exists. Fine. Oh, yeah. And now we also have to sort the tokens for consistency, but the pair for this combination, if it already exists, so we have to like write it as, address 0, like it's 0, 0. Okay. And then we're going to sort things for consistency, where we say address token 0, and then we say address token 1. Okay. Is equals to token A. Again, that's done. Token B. Ternary operator it is, and we question mark, and then we say the pair is gonna be a token A, token B, or it's gonna be the opposite, which is token B and token A. Come on, now you've understood how the ternary operator works, right? And then we say that the pair is gonna be address, and then we say new MiniDex pair. That's how we're creating a new instance, and we say token 0, comma, token, token 1, right? And then we say get pair token 0, okay, token 1, okay, is equals to pair, right? And then the same thing the other way around too. So we say get pair make this token 1, make this token 0, and then pair. Okay. Now what we do is push this in all pairs. So we say push, pair, create, emit, pair created. Okay. Token A. No, this is token 0. Oops. Token 0, token 1, and the pair, this is just pair, and then we say this one is going to be all pairs dot length -1. Wow, what did we just do? Check the access control, because only the owner of the factory can call this function basic validations so that the pair does not exist already. Token sorting, again, very subtle but very important. We always store the pairs in the order token 0, token 1. So we have to ensure token 0 less than token 1. So we have to, now this is done so that DAI and ETH is gonna be same as ETH and DAI. Same pair, right? Our mapping works in both directions. So front end and indexers don't get confused. Now you're deploying the pair contract by creating a new instance of the MiniDex pair contract using the sorted tokens. This is the actual on-chain liquidity pool that we're talking about. And then we're storing the pair in both formats, right? So store the pair address in the mapping under both combinations, add the pair to our all pairs array so it can be indexed, and then emit the event. Great, right? Now, I think this was the only major function, and then we'll do a view function. So we say all pairs length is gonna be external view returns. Okay, returns what? uint, and then we say return all pairs dot length. Okay, so you know how many pairs are already listed on your DEX, and you're gonna get rich because the DEX is getting popular. Get pair at index, right? We say uint index, right? And we say external view returns, and then we're going to return the address, and then we say we also have to check. So the index has to be less than all pairs dot length, because otherwise the pair index would be out of bounds. Very smart AI. And then we say return all pairs at index. Yep. Great. Nothing to explain here. Total number of pairs and get the pair at a particular index, right? Like the first pool that we've created was token A, token B. It could be DAI ETH, W ETH, whatever, right? Now, how are you supposed to run this MiniDex factory plus the MiniDex pair in Remix? Okay. Create 3 files. Again, we had mock token.sol, we had minidex pair.sol, and we had minidex factory.sol, right? We've already deployed 2 mock ERC20 tokens, right? For example, token A, token B, great. Now we have a note of their addresses. With minidex factory, we have to deploy it, and we say, okay, wait, let me show you, compile. And then if you come here, okay, let me close this. This is token B, this is token A, this is MiniDex pair. And we're saying address of the owner, right? So give the ownership of the factory to your current account in Remix, right? So we say, fine, this person is the address. Great. Transact. Fine. Okay. Now you have to create a pool using the fact. Okay. Create pair, address of token A, address of token B. Okay. So what happens is I'll take token A. You can change the name because we've already talked about these 2 tokens. No, maybe change the name there and get some other tokens here. This is token B. Now you transact. So what will happen is this factory will deploy a new MiniDex pair contract, save it in the registry, and emit a pair created event. Okay. So to get the new pair address, you can use get pair, token A, token B, or get pair at index 0. Now you can deploy with the, interact with the deployed pair, but let us see what happens. I say create pair. Fine. Okay. Token A, token B, 0, address pair. So we're saying get pair at index 0. Great. This is what we're getting, right? All pairs. Fine. This is the address that we're getting, right? Now, okay, get pair. If I copy this, and then I copy this. Boop, same thing. Okay, that is the pair address that we're getting, right? Now that the pool exists, you have to copy the pair address from the factory, go to the deploy and run panel in Remix. So just copy this, right? This is the pair address, I think. Yep. And then paste the pair address and select MiniDex pair. Yeah. So we're saying this. We're saying MiniDex pair load contract from address, right? And now you can just directly interact with the pool. Now you see a new one was created, right? We had a MiniDex pair here, but here it was created, right? Now if you check the total LP supply, it's 0 because we did not add anything, right? So then you have to approve the pair contract to spend tokens, okay? So now you need to copy this pair address and then go to the tokens, mock tokens for both the tokens to approve that, you can just add the amount. Like, for example, I will show you. Here, what we were doing is we were adding liquidity, right? Because we'd given access. So now let's try doing this here. I say add liquidity. Fine. This should work, right? Because token A, token B was deployed before. Can I try it? Great. No, right? Without being their owner, amount of tokens the spender is allowed to operate with. That is why we have to come here, go to these token. Okay. So we've changed the spender here. This is going to be, so transact, and for token A, same thing. Paste, transact. It goes through. Now try adding liquidity. Fine. Now total LP supply. Great. Reserve A, reserve B, token A, token B. Wow. Get reserves, get total supply. So you have it all, right? Now, this is how you've added liquidity. You can get your LP balance, total LP supply. Let me get the balance. You can do it from different accounts as well. Where is it? Yeah. Yep. That's your entire balance, right? Then you can say, get reserves. We've already done this, right? So from the same pair contract, again, approve again from a second account, call input token, like do a swap, remove liquidity, explore and monitor and have fun. And yeah, that's it. That's it for 30 days of Solidity. I really, really hope that this was extremely, extremely helpful for you guys. We would want you to tell us what is it that you expect from the community more, what should we come up with next, and how can we help you in the development journey. And we're really, really trying to do some interesting stuff here, but we'll talk about that later. And thank you so much for being with us in this journey. And if you're not on our Telegram group, or you just hop on, ask us questions, DM me at Audacious Sneha, DM Setu. We're happy to answer your questions anytime. And see you guys again in the next campaign. Till then, happy building.